Okay, welcome back. Oh, by the way, I forgot to explain one point about whether when diode turn on, whether the energy stored back to the capacitor in reverse polarity or not. To check that, you need to find the current IL, and then here IL here, and then you find the current IC to see whether IC is negative or not. Okay, or you can also find VC. If VC is negative, then you can see that the voltage, you can see that energy charge back to capacitor in reverse polarity. Okay, and next let me continue to the next lecture, which is lecture 4, DC-DC converter. Okay, so in this lecture I'll cover 4 main points: analysis technique, direct converters, which have 2 type of converters, and then switch implementation, and the last one, indirect converter. Okay, first about analysis method. We use Kirchhoff current law at a node, so the instantaneous current flow through branch 1, 2 up to n, and all of this current flow through a node. Then we can have Kirchhoff current law as the sum of all the current equal to 0. Okay, this is Kirchhoff current law, and then if we average all this current over time, I mean each one of them, let's say if current I1, I2 or IN are periodic, okay, periodic with period capital T, then we can find the average by applying the integral over the period T. So because the integral of sum equal to sum of integral, then we can have the sum of average value of current into a node equal to 0. Okay, so here you can see sum of instantaneous current, and this one is sum of average current. Okay, still 0. So Kirchhoff current law can be also applied for average current. Next, Kirchhoff voltage law. You have a loop, so the sum of voltage in a loop equal to 0. This is sum of instantaneous voltage. Then again we apply the average value over a period time t. Finally we can have Kirchhoff voltage law can be applied to average value of voltage as well. So this is summary for periodic steady state, Kirchhoff current law and Kirchhoff voltage law. And previously 2 weeks ago I already explained why the average voltage on an inductor is 0, right? Because the periodic steady state, you have current as the periodic function, then time derivative, its time derivative become periodic function where the average value is 0. Similarly for capacitor, the average current flowing through capacitor is also 0. Okay, because voltage VC is periodic, then time derivative is periodic with average value 0. So this is what you need to remember. Average voltage of capacitor of inductor is 0. Average current of a capacitor is 0 for periodic steady state condition. And for most of our analysis, we consider circuit is lossless, which means we use the relationship power output equal to power input. So first, let's see a direct converter. Okay, consider this direct converter. So here you have input voltage V1, okay, output voltage V2 at load, and you have filter elements such as inductor and capacitor. So when I say filter, if you still remember well, this element try to smooth the output current and voltage at the load V2. And in order not to waste energy, we implement switching technology, right? In order to have lower voltage, for example, lower voltage at the load than voltage at the source, we use switching technology. So Q is a switching function, which is in practice programmed by microcontroller. And let's assume all the filter elements are big, so the voltage on the output V2 is approximately constant, and the current, okay, voltage at C here same as voltage V2 here, and the current flow through the inductor L is approximately constant as well. I think I should have this graph first. Yeah, so let's say we implement the switch function this way. We turn the switch to 1, which is too close to this branch from here to here. Okay, from here to here. Then what happened? Then the voltage VH here, control L. Yeah, voltage VH here is the same as voltage from capacitor here or from the input source here, which is V1 here. Okay, control P. Yeah, V1. And then we switch Q to 0. Here, which is to connect from up here to here. Okay, 0. So the voltage VH here is short, right? We short, so it's 0, like this. And we repeat it periodically with time period T, capital T. And now let's draw VL, the graph of VL. So we draw in 2 segments, just 1 period. So we have dt here, and then we have capital T here. Okay, first when Q is 1, it connect to here. VL equal to what? VL equal to V1 minus V2, right? Because we can see this loop. So VC1 and V1 is just the same, and VC2 and V2 is just the same. So just ignore VC1 and VC2, just say V1 and V2. So voltage in here equal to V1 minus V2. Red one. Okay, V1 minus V2. Then let's consider the case Q equal to 0. So VL here and V2 here, we are in this loop. Now in this loop, VL equal to minus V2. So I use the blue one. Okay, it's minus V2. Well, then we can use the analysis of periodic steady state, where the average value of VL equal to 0, right here. Average value, which is we can be found using the integral over the period, right? So the average value of VL is 0, implies the area under this curve equal to area above this curve. Okay, so this is minus area, this is plus area. So this area can be computed this way. One side is dt, okay, from 0 to dt here, and another side of the rectangle is V1 minus V2. How about area, the negative area here? From this period from here to here, you have t minus dt, which is 1 minus d times t. So one type of rectangular is this, another side of the rectangular is minus V2 here, minus V2. Then we add them up to be 0. Finally, because this is 0, finally we can find a relationship between V2 and V1. Actually, V2 is just equal to D times V1. What is D? If you look at here, D times T is less than T, which means D is always less than 1 and it's greater than 0. Okay, do you have any question up to this point?
D is time, right?
What?
D is time.
No, D times T is time. D is just a fraction.
Yes.
Because D times T can taken between 0 to T. Here is 0 and here is T. So D times T is always in between this, which means D can be taken from 0 to 1.
Yes, I get it.
And similarly, we can apply the average value of current on the capacitor IC, capacitor C2 here, C1 and C2. Then finally, we can find I1 equal to I2. Okay. So, of course, it has to be this way. Why? from the energy conservation, the power from the input equal to power on the output. So this relationship, yeah, we have I1 equal to dI2 and dV1 equal to V2. If we multiply left hand side together and right hand side together, finally we have the relationship as power in input equal to power at output. If we consider lossless element, lossless circuit, so we consider as an ideal case. So in analysis, to have a simple analysis, we need to start with the ideal case like this. Okay, now let's see a converter, so-called buck converter. Buck means down converter. So you convert the voltage V1 to V2, which is less than V1. Then you call it buck converter. And here is to implement the switch. You use one transistor here, MOSFET actually. This one is MOSFET. And this one is diode. So why we can say this is the same as switch function that we analyze here? We need to verify that it can have function that can switch to here and then can switch to here. If we can send the signal to the control gate in this way, right? We call pulse width modulation. Pulse mean the waveform is rectangle like this, rectangle and then drop and then rectangle. So we call it pulse. One period is one pulse. Width modulation means we can program to whether to have duty cycle D small like this or big like this, right? Or even big like this. So we can program to change the duty cycle taken from 0 to 1. That is modulation. So let's confirm or verify that the switch implementation can function to be connected to here or here. Let's see. Well, let's say if I send a signal from microcontroller as a pulse like this through the control gate here. So the function of MOSFET is that when you have a positive voltage or logical 1, positive voltage represented by logical 1, then this one is on, it turn on. So when it's turned on, the voltage from here is high, potential here high and here is low. So potential push this way, but diode block, right? Block, not allow current to flow this way. So you have only this circuit. So you can use the analysis only on this circuit, which is the same as here we analyzed before, where you have VL as V1 minus V2 here. And then when the signal sent through the gate here as 0, then this one is open. When this one is open, because energy is stored in here in the inductor, it continues to spin the magnetic flux and sucking current out from this way, but not from here because here is open. So it sucks from here. Okay, sucks current from here. So it's like you have when this one connect to here, right? Same thing, and you analyze the circuit just like this. Oh, sorry, should be here. Yeah, like this. Then you have voltage here minus VL equal to minus V2. Is it okay? Can you understand this? Woodley?
Yeah, teacher.
Bullstrom, you have any question? Because this is very important. The first converter that you learned.
That's a question.
Okay. Next, let's see boost converter. It's very simple actually, because in the previous converter you have from here you can look at this, it's still the same, it looks same. So, and what you have is that this voltage here larger than voltage here. So now we just switch the side. Okay, switch the side of the load and source. So now load is here, and source is here. Okay, source V1, and but also we change the switch function. Switch function 1 is here, 0 is there. Okay, previously 1 is up here and 0 is down here. Just change switch function like this, and again we still have control pulse width modulation in this way. Okay, 1 0 1 0 like this. Now let's make analysis. When the switch function is 1, we connect to here. So the voltage VL equal to V1. Okay, VL equal to V1. V1. No, let's see VH first. Sorry. So VH first. So VH, because here is short, VH is 0. And then when we switch from here to here, VH is equal to V2, same as here. V2 here. And it repeats. Look at VL. When the switch connect to here, we look at Kirchhoff voltage law. So VL we use the plus from this side, okay, not from this side. See, plus on this side. So let's say from minus to plus, let's call it VL, and then plus to minus would be minus V1. So here we can have VL equal to V1 here. Then the remaining period we switch Q to this way. So here switch function is 0, VH is V2, and then VL we have, okay, V2 we have this loop, V2 minus 2 plus VL minus 2 plus, so plus VL, and V1 is plus to minus V1. So VL equal to V1 minus V2. So V1 minus V2, we can say that it must be negative. Why? Because periodic steady state says that the average value of VL has to be 0. Average value of VL has to be 0. So part of part of the time VL is positive and part of the time VL is negative. Okay, so now we use the periodic steady state condition. Every value VL equal to 0. Then we find the area under the curve, which is the area of this rectangular plus area of this rectangular equal to 0. Okay, this is the area of this rectangular, and this one is area of this rectangular. And finally, we can find the relationship between V2 and V1. And here you can see that V2 is larger than V1. Why? Because D taken from 0 to 1. D. So 1 minus D would be taken from 0 to 1 as well. So minus D. So I have 1 less than 1 minus D. Okay, greater 1 greater than 1 minus D and greater than 0. And then I inverse all of these. I can have 1 less than or equal to 1 over 1 minus D less than infinity. Okay, so we can have because this term is always greater than 1, then V2 is always greater than V1. Is that okay, Vadana?
Yes, teacher.
Oh, this one is no. Okay. Now let's see switch implementation. Okay, and switch implementation here, but now just flip the schematic from this one to this one. See, right? V1 here, and inductor and C2, inductor and C2, and then the switch implementation here, and we have load here. Okay, just switch to have a convenient look on the circuit. So let's analyze the switch implementation. Here you have a MOSFET again, and here you have a diode. Let's say I program from microcontroller to send the signal as a pulse like this. To control the gate here, right? This is gate. Switch function is 1, represented by 5 volts, for example. QT. So when 1 is sent, then you have 5 volts at the gate. You turn this one on. Then you have a circuit, the closed circuit like this. You can make analysis using voltage, Kirchhoff voltage law, right? And because here has a small resistance, very small, yeah, ideally small, let's say. So current does not flow this way, but only flow this way, because here it will go to a resistor here that has larger resistance, so it does not want to go there. If this resistor is ideally 0, 100% current flow this way. Then during the period that switch function is 0, you send 0 voltage to the gate of MOSFET, then it is off, so it's open. Then the energy stored in the inductor here, okay, the spinning or magnetic flux keeps spinning, so it discharges the power to the load here, so this way, okay. So then it repeats, okay. Close, charge energy. Open, release energy. Okay. Close, charge energy. Open, release energy. Repeat all the, as long as you send the signal to the gate. Now we can see that we can have power flow direction, right? Power flow direction which depends on external network, switch implementation and control. So this the short conclusion drawn from our two converters, bucks and boost, which means we can have power flow direction from lower voltage to higher voltage, or from higher voltage to lower voltage, depends on external network. External networks means how you have a network, a circuit that you can send the signal to control the MOSFET. And it also depends on switch implementation, how you construct the MOSFET and diode, and how you control. How you control means when switch function is 1, when switch function is 0, and duty cycle, or how much duty cycle you send to control the MOSFET, something like that. Is there a question? Radi, Lee Radi, do you have any question?
No, sir.
Okay, then I continue to the next part. Okay, let's take a look at this canonical cell, which means if you have this cell, then you can use it to construct buck and boost converter. It just it depends on how you connect, right? You connect A, B and C. So like because here is a switch on and off, and C connect, if you connect it to the source, and A you connect to the load, B you connect to the ground, then you can have a boost converter. Okay, and you flip the circuit, okay, source on this side and load on this side, and then you can have buck converter. Yeah, you can play around this to have boost converter like this, and to have buck converter like this. Now let's take a look at switch implementation. So different switches can carry current and block voltage only in certain directions. For example, here First you have MOSFET here. MOSFET can block positive voltage and can carry positive or negative current. Because here this is equivalent schematic. You can command to switch on and off in here. So actually current can flow the negative freely through this branch. By the way, when I press like this, do you see the sign of eraser? What now? What now?
Yes, sure.
Do you see the eraser when I press like this?
Yeah.
You see the pointer, right?
Yes,
Yes, teacher.
I
I
can
can
see
see it.
Okay. So current can flow in the negative direction freely through this branch of diode. And for current to flow in the positive direction, you need to switch it on. And for the voltage, it can block on the positive side only. When you switch this off, you can block voltage because this diode automatically block the voltage from the positive direction here. Positive direction means for this one. Next you have bijunction transistor. So this one is similar to MOSFET, but negative voltage blows up the device. It does not have the parallel diode like this to allow current to flow upward. So if you use a wrong polarity of voltage, you just blow it up. And same for IGBT. Then you can use combined elements because IGBT does not have diode inside. Then you combine diode from outside like this, so it can have function like MOSFET here. Okay. The next one, you can also protect IGBT using diode this way, but the difference from the previous one is that it cannot conduct negative current. Okay. Because the diode block the current this way. So voltage is blocked on both positive and negative. Current can carry only on the positive direction. For this switch, well, this one you can block both positive and negative voltage, and you can allow current to flow in both directions, but you need to control on two gates. You have gate 1 here and gate 2 here. You can control current to flow from up to down here by this way, by switching on G1, and you can control the current to flow from down to up by controlling the gate 2. Okay, so I think I'm gonna stop now because I don't feel so good. But anyway, do you have any question? I can take a few questions if you have. Sitai, do you understand this switch implementation? Sitai, are you here? If you are not, if you don't answer, I assume that you are absent.
Teacher, he is here, but he cannot use his mic.
Oh, okay. I see. Boromai? Oh, Boromai is absent, I think. Lisa, do you understand this switch implementation?
Yes, teacher. We have question.
Okay, so let's end our lecture today.